Hello, everybody. My name is Jadea Hudson. Welcome to Lab 3, Black Hole. Now, introduction. The purpose of this lab is to find the mass of a black hole by analyzing a star's orbit and use the information to find the initial velocity your ship that will be given later must have when it leaves the surface of the planet that we're given later to fly around a black hole without crashing on the planet or the black hole. Fundamental principles that we'll be using are the momentum principle and Newton's universal law of gravitation. And our early look at the results are that the mass of the black hole is 8.341547 times e to the 33, and the initial velocity of our spaceship is x going to be equal to negative 3.948 times 10 to the 7th and 2.97 for the y times 10 to the 6th. Now, our main ideas are universal gravitation, Newton's second law, the momentum principle, and we're going to be assuming that the magnitude of our net force is going to be equal to the magnitude of our force of gravity. And then we have here the magnitude of force of gravity equation, and we're going to have that worked around to find the mass of our black hole. Now, system and surroundings of our first part of our lab is that the system is going to be the black hole and the surrounding is going to be the star. Our initial conditions are that the mass of the star is 2 times 10 to the 30, and that's going to be kilograms. And the first timestamp is going to be t equals 0, and our gravitational constant is going to be 6.7 times e, which is 10 to the negative 11. Now, this is all of our code to help us find the mass of our black hole, which is going to be very useful. We have to find things like the velocity and change in momentum. We also have to calculate F-net. There's a lot of things that we have to find first before we can truly find what our mass of our black hole is going to be. Now, over here, find the mass of the black hole. We can see that after doing the summation, which I coded in but didn't show you because it was not too pretty, that the mass of our black hole is going to be 8.364154739984767 times 10 to the 33, and our other results are all going to be not our unit vectors, but they're all going to be the magnitude of these forces: F net, the net force, the parallel force, and the perpendicular force. Here they all are. Moving forward, now we have part 2, don't crash. Our initial condition for this is that, well, we have a lot. So first, we have gravity, our gravity constant in space. Then we have planet's mass, ship's mass, delta T is going to be equal to 1. And we have planet speed, planet velocity, some things that they already give us. We also have from our part 1 the mass of our black hole, which is given to us right here. The system and surroundings. The system is going to be our spaceship, and the surroundings are going to be the planet and the black hole. Calculating the net force of the spaceship, it took a lot, to be honest, but here we have the force of gravity on the planet by the spaceship is right here. We calculate this all right here, and then we move forward to go force of gravity on the spaceship by the black hole. It's right here, and it's going to be on by the planet, but we combine all of that later to find that the initial velocity of our spaceship and the x component is negative 3.948 times 10 to the 7, and y equals 2.97 times 10 to the 6. Also, this little curve right here was so funny after doing all my calculations. I mean, I'm right, but like, geez, why I only get that curve? Now, our possible source of error are that human error while inputting numbers into the code causing incorrect value yields are a possible thing that may have been a source of error, and our what if and what does this mean? Now, what does this mean? In your analysis, you should discuss how net force and its parallel and perpendicular components are different from the rate of change of momentum and its parallel perpendicular components. Now we have that F parallel is parallel to the direction of motion, and F perpendicular is perpendicular to the direction of motion. That is their differences. Now they're different from our net force because net force is the change of momentum over change in time. It's the change of momentum over change in time, which can be drawn out as mass times acceleration, which is all the forces acting on the system, versus perpendicular and parallel forces are parallel and perpendicular respective to our net force. Now we have our what if, and it's basically saying, what if we wanted to orbit our black hole? And I was not able to find what that would be. But thank you for your time.